In this video, I'll be talking about one of the types of logical arguments, one that's based upon the logical connectives of and or, and not, and conditional and biconditional. There's another type which is based upon quantifiers. That won't be in this video. I will be making another video on that. But first of all, to understand, valid arguments are not valid because you agree with the results. They're valid because the logic flows nicely. So I could say, for instance, I could say if someone is elected U.S. President in 2020, he is at least, or he, she, you know what, let me make this 2200, I meant to do that. Make that 2200 so we have no idea who's running. Okay, so he or she is at least 35 years old. And then we say, okay, so he won, so he is at least 35. Now that's an argument, and it has some supporting statements, and these are called premises, and it has a conclusion. Now, in determining whether something is valid, we're really only looking at the logic behind it. We're not trying to say whether something is actually true or false, or whether any one of these three sentences are true or false. Doesn't play into whether the argument is valid. I mean, I have no idea who's going to run in 2200, neither do you. And I have no idea whether the present law for who can run for president, one of those says you have to be at least 35. If those are going to be the present, or if those are going to be the laws in 2200. So I don't know if any of these things are true. I can talk about whether this argument is valid. But to illustrate that it's really the format of the argument that makes a difference, I'm going to put another thing that has the same format. So, if pigs can fly, I'm a billionaire. And, excuse me, pigs can fly. So, I'm a billionaire. Okay, these, I don't think you agree with any of those sentences. I don't. But it has the same format. You see, we started out with a conditional statement. That was our first statement. And the second is that the part that's before the arrow, to the left of the arrow, okay, so this is the part to the left of the arrow, and the conclusion is the part after the arrow. In simple form, both of these will look like P, arrow Q is the first sentence, P is the second sentence, and Q is the conclusion. They both look like that. So they're considered to be the same as far as determining whether it's a valid argument or not. Now, there's going to be 6 standard types of arguments. These occur often enough that they've gotten names, and I'll talk about those, and then I'll talk about what happens if it's not one of the 6 standard types. All right, so I had talked about George winning the 2200 election, his being 35 years old, and here's the argument. And I said this is actually one of the standard types. And this is called the Law of Detachment. And these are valid arguments. So any argument in which you start out with a conditional, and then your other supporting statement is the part that comes before the arrow, and your conclusion of the thing after, those are all called laws of detachment, and those are all valid. So let's look at some of the others that involve arrows. So if I have P implies Q, and I'm going to switch these two, and I'll put a Q here, and I'll put a P here, then I've got another argument slightly different. This one is actually invalid, and this one is called the fallacy. Fallacy means a wrong argument, wrong thinking. Fallacy of the converse. So, reading out loud, if George wins the 2200 election, he is at least 35 years old, and then you say he's at least 35 years old, therefore he won the election. Not so. It's not true in any election. There's plenty of people over 35 years old who never won the election. So, okay. Just because both of these things are true does not mean the third thing must be true. The truth of the last thing does not flow from the truth of the first two. Okay, another fallacy would, if I start out with my conditional, same conditional, and this time I'm going to say not P, and I'm going to say not Q. So if George wins, he's at least 35, at least according to present law. But he didn't win, so that means he's not 35 years old. Of course, that's not right. And that is an incorrect way to reason. So it's a fallacy of the inverse is what it's called, and it's invalid. Okay, and I got room for one more on this board. So these four are usually kind of talked together because they all have that P implies Q, and then the second sentence has something to do with this. Whether it's the thing before, the thing after, or it's the negation of the thing before, or in this case, it's the negation of the thing after. And this one is called the Law of Contra Positioned. And this one is valid. So it's not in my videos, but there is something called a Contra Positive, which is considered to be the same as the original. So this P arrow Q is considered to be the same as a not Q arrow not P. And so if I were to replace this with its same thing, you would find the second sentence is the thing before the arrow, and the conclusion is the thing after the arrow. Since I'm allowed, since these are considered to be exactly the same from a logical perspective, since I'm allowed to swap one with the other, yeah, after I do the swap, it's called Law of Detachment. Before I do the swap, if I don't actually write that swap down, it's called Law of Contra Positioned. Trying to remind you, yeah, it is valid because of the Contra Positive. Okay, so I've got those four. Now I've got two others I want to talk to you about. A fifth type of argument, one that is seen often, has two conditionals for the premises and a conditional for the conclusion. And notice it starts with P, ends with Q, and then the next one starts with the Q and ends with an R. So actually what you're doing is you're going, I can go from P to Q, and from Q I can go to R. And what this is trying to tell you is I can go from P to R. So if you got the arrow set up this way, it's possible to go all the way from P to R. That's what it's trying to tell you. In the words that I have here, if George does win the 2200 election, then he's at least 35 years old, because that's the law. And if he's at least 35 years old in 2200, then he is alive in 2190. Okay, that makes sense. And now this says if he wins the election in 2200, he was alive 10 years earlier, of course. But no matter what P and Q and R stand for, this statement will flow logically from those, and this is called a law of syllogism, which I always thought was a really silly name. Oh, and it's valid. I thought it was a silly name because actually all of these are syllogisms. Syllogism just says you have two premises and one conclusion. That's all it says. I don't know why this one got called Law of Syllogism and none of the others did, but that's its name. Okay, one last one, and this is a pretty easy one, and I won't use the P's and Q's and R's. Not those P's and Q's and R's. But the first statement is either P is true or Q is true. All right? The second statement is P is not true. And then the conclusion is that Q is true. So, yes, this one sets up saying one or the other is true, and then you've eliminated that choice, so the only choice left with that. All right. Yeah, so this is law of disjunction, or disjunctive, excuse me. I have this a little bit off, but this is valid. So those are 6 types of arguments, 4 of them being valid, 2 of them being invalid, that you might see often. But what happens if you have an argument that's not of these 6 types and you want to determine whether it's going to be valid or invalid? Well, you're going to have to use the truth tables. And in the truth tables, we're going to look at every single possibility, because that's what truth tables do. And we're going to see, is there any time when both of these things are true, when all the supporting arguments are true? Is there any time all the supporting arguments are true, but the conclusion is not true? And if that's possible, then we can't possibly say that the conclusion flows logically from the premises. If to put it another way, if there is ever a time when in all the lines of a truth table that you see both premises true and you see the conclusion comes out false, you can immediately say, no, that's invalid. On the other hand, if every single time and every single line that your premises come out true, your conclusion also comes out to be true, then you say, oh, it's valid. So we're going to do this one, and then I'll do something that's not one of the 6 standard types. Okay, so I'll show you a truth table for this thing, which we know it's valid. We know it will come out that in any line in which both of these things are true, that thing will come out to be true. Because we said it's valid. It's got to be that way. And then I'll give you an example of an invalid argument. Okay, so to set up a truth table, you actually have several truth tables going on at the same time, one for each sentence. So I've got my variables, my P and my Q, and because there's 2 variables, I need my 4 lines. And then I'll set up each of these sentences in a separate column. And then I start working them through, and again, I'm looking for cases where both of these 2 are true, but this one comes out to be false. If I find a line where one or the other of these is false, I can just stop. I don't need to worry about that line. That line doesn't matter. So, for instance, let me say I look at this, and that's not P. So I go false, false, true, true. Okay, I know I don't need to worry about these 2 lines, the first line and the second line, because I'm looking for times both of those are true. Not going to happen here. So I don't have to worry about that line. I don't have to worry about that line. I don't have to fill out the rest of it, right? I'm saving myself some work. Okay, now let's take a look at the P or Q. So P or Q, you look for the exception. If you have false or false, I do have it here. And then everything else comes out to be true. Okay, so I need both of the premises to be true. Because that happens, I don't have to worry about this line. Okay, now what about the conclusion? There's only one line I have to worry about, and in that line, the conclusion is true. So I can see that every single time, there's only one of them. Every single time, both premises are true, the conclusion comes out to be true. So valid. I'm just writing this out. Whenever the premises are all true, the conclusion is true. So valid. Okay, so now I'll erase that and I'll put up another truth table that will come out to be invalid. All right, so now I'll actually have three variables in this example. So P or Q implies R, and then P and R. And you might realize why this goes wrong. This says, oh, I'm sorry, I meant to say an and here. And. This says you have to have both P and Q being true in order to know that R is going to be true. And the second sentence says, you know P is true. So you know what? You're not quite certain whether R is going to be true or not. Okay, so I'm going to need three variables. Actually, and I sort of erase this. I'll do this very quickly. Okay, so I need 8 lines with 3 variables. 1, 2, 3, 4, 1, 2, 3, 4. True, true, false, false. You know, so this goes every 1, 1 true, 1 false, 1 true, 1 false. This goes every 2. And then this one goes every 4. And I tend to draw lines across so I can keep track of which row I'm in. Okay, so I'm going to put down both my premises. And I'm going to put down my conclusion. And we'll run through this truth table. And again, I'm going to look for things where all the premises are true. And I might work with P first. That's going to be very easy because I can just copy that down. And I can immediately eliminate 4 of the rows because I'm looking for rows where both premises are true. So that's not going to happen in the last 4 rows. So I don't need to fill out anything else at all in the last 4 rows. They're not going to be what I'm looking for. Okay, so let me fill these out. And I have to do the and first because of the parentheses. And then I would do my conditional. So P and Q, if both of them are true, it comes out true. There's a true, no, and no. Okay, so those both come out to be false. And then I'm going to do the and, compare it with the R. The and is on the left. I'm looking for any time there's a true on the left, a false on the right. Does not happen. It happens here. Remember, this is on the left. True on the left, false on the right, so this comes out to be false. No and no, so these all come out to be true. Okay, I can eliminate, and this is the final column for my first premise. So here's the answer to my first premise, and it does have a false, so I can eliminate that row from consideration. Now, R is easy, I just copy it down. So is there ever a time when both premises are true and the conclusion is false? Yes, right here, this one. And so I say invalid. It is possible to have this statement true and this statement true, but that statement false. So how in the world can that logically follow from those? It can't. So you say invalid. Okay, so we either have the 6 standard types, and you'll be expected to list them by name if they're one of the standard types, and you'll be expected to know whether they're valid or invalid, or you can do a truth table. Now, if you're really poor at memorizing, you can actually do the truth table for the standard types, right? You don't actually have to memorize the standard types. You could just always do a truth table, but that's a lot more work. Okay, thank you so much.